science. Is everybody excited for this conference was led by Mexico? Now let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. ICPS. Welcome you all to our ICPS conference. Is everybody ready for days of science from Mexico? Now let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. It's time to share your great knowledge of this science. Is everybody excited for this conference was led by Mexico? Now let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. ICPS. Welcome you all to our ICPS conference. Is everybody ready for days of science from Mexico? Now let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. It's time to share your great knowledge of this science. Is everybody excited for this conference was led by Mexico? Now let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. ICPS. Welcome you all to our ICPS conference. Is everybody ready for days of science from Mexico? Now let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. It's time to share your great knowledge of this science. Is everybody excited for this hosted by Mexico. Now let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. ICPS.
So Dr. Ivette, I have to tell you something. I think there were people waiting.
Welcome you all to our ICPS conferences. Everybody ready for days of...
And I am the scientific program coordinator of the ICPS, International Conference of Physics Students, Puebla 2022. It's a great pleasure for me to introduce our next guest speaker, who is going to give us a talk about exploring the unification of quantum theory and general relativity with the Bose-Einstein condensate. So Dr. Fuentes' work in theoretical physics aims at finding grounds where quantum and relativistic effects can coexist in a compatible way. She applies novel techniques for information theory and metrology to find ways for quantum matter to explore the underlying spacetime. She obtained her bachelor's degree in physics from the National Autonomous University of Mexico and her PhD from Imperial College London, and held academic positions at the University of Oxford, the Perimeter Institute in Canada, Technical University Berlin, Germany, and the University of Nottingham in the UK. She has worked with the expressionist artist Benjamin Arismendi on an art science project entitled The Aesthetics of Entanglement. Without further ado, please join me in welcoming Dr. Ivette Fuentes.
Thank you very much. It's a wonderful pleasure to be here. Thanks to Melissa and all the other organizers for this very nice invitation. I'm very excited because I am in Mexico City at the moment after 3 years of not being able to come to my home country. And when Melissa sent the invitation, I was very excited. I was like, oh my God, I'm going to get to go to Puebla. So unfortunately, it's still online, but well, it's nice that in this way we can reach people in many other places. So thank you very much. So I'm, yes, like Melissa was saying, and thanks for the nice introduction. I work at the interface of quantum mechanics and general relativity. And one of the things that I do that is, let's say, a bit new is that I've introduced techniques from quantum information and quantum metrology to try to address some of these older questions, let's say. So let me start with the motivation to my work, and then I'll tell you about some of the results. So by the way, I don't know how it works in terms of, I'm trying to move my, okay, yes. But how it works in terms of questions, but from my side, if you want to interrupt and I ask a question, that's totally okay. But I guess the workshop has already its rules, so we'll stick to that. So I want to start by thanking all the former members of my group, postdocs and PhD students. I'm going to tell you about group work that has been sort of accumulating and building up for many years. I started working in the overlap of these two theories in 2005. So many wonderful students and postdocs have contributed to this work, and also collaborators. So there are many fundamental questions that are very interesting in physics that still are unanswered. So just to give you some examples, we don't understand what is the nature of dark matter. It's important to find out if dark energy is driving the accelerated expansion that we see in the universe. We're also trying trying to find what is the physics of the early universe at very early times. And let's say in quantum mechanics, it would be also important to understand if the equivalence principle still holds for quantum systems. So yes, so it's very interesting, but underpinning many of the interesting fundamental questions that we have in theoretical physics at the time is our difficulty to find a theory that allows you to describe physics at scales where you would expect quantum mechanics and general relativity to interplay. So we say these two theories are incompatible, and not being able to find a compatible theory that incorporates both is really underlying many of the difficulties finding answers to the questions that I just mentioned. So we've made a lot of progress mathematically. There's different proposals and different theories like loop quantum gravity or string theory, quantum field theory, and curved spacetime, and all on, but they're like pieces of a puzzle that don't really fit in together. And the consensus is that we haven't really found yet a theory that allows to describe the effects in a compatible way. So on one hand, let's talk a little bit about the theory. So in quantum theory, time is absolute. And as in our experience, space and time are very different notions. In quantum mechanics, time is a parameter, whereas space positions are given by operators, and you can quantize positions. So you can see how in quantum theory, space and time are treated fundamentally in a very, very different way. And then we get effects in quantum mechanics, such as particles can be in a spatial superposition at the same time. So you can have a mass being in two different places at the same time. This is, of course, modulus the interpretation of quantum mechanics. I guess most of you have taken a course in quantum mechanics, and you know that we're still not being able to interpret what our mathematics mean exactly, no? So, but one important feature of quantum mechanics is superposition. On the other hand, in relativity, time is observer dependent. So the clocks tick at different rates depending on the state of motion of the observer. And actually something that is really radical about relativity is that we learned from Einstein is that space and time are really not that different. They actually belong together in a higher dimensional object that we call space-time. And then when we have mass curves the space-time, and you can get at different points in space that time flows at different rates. So we can imagine how complicated it would be to describe effects such as, for example, having a mass in a superposition of two different places in curved space, where time in the different regions is going to be flowing at different rates. So we still cannot explain this sort of effects. But the most important question, in my opinion, to be answered is if space-time can be in a superposition of two different configurations. Now imagine you have a massive system, and if you could put it in a superposition of two different places, well, the mass curves its space. So if the mass is in a superposition, this would mean that the space-time configuration is also in a superposition of two configurations. And we don't know if it's possible to do that. So this is very interesting, because actually we do know from the experiment that the electromagnetic field can be in such superpositions. The electromagnetic field can be put in a quantum state. So if you have a charge in two different places at the same time, the charge generates an electromagnetic field, and you see that the electromagnetic field is indeed in a quantum state. But we don't know if gravity for example, is different, fundamentally different to the electromagnetic field. And we have some good reasons why to think it could be. And that's because only gravity obeys an equivalence principle, not the other forces. So that could, in principle, make gravity different. But we're trying to understand if that's the case. So Roger Penrose likes to pose the question as, should we quantize gravity or quantize quantum mechanics, or gravitize, sorry, quantum mechanics. So let me explain what that means. Quantized gravity would mean to keep the principles of quantum mechanics and then maybe change general relativity in order to help us fit in the two theories. Or Roger prefers and thinks what we should be doing is more like gravitizing quantum mechanics, which would be to keep the principles of general relativity, but then change quantum mechanics. And he thinks that because quantum mechanics already has a problem, which is the measurement problem, that already points out to us having to come up with a, let's say, more fundamental theory that incorporates quantum effects. Most likely, and what I think, is that we ultimately will have to modify somehow both theories in order to find a way to bring them together. But which principles should we keep? Which are more fundamental? Well, we need experiments to give answers to that. So I think we're at the brink of very exciting times in which experiments that are just being possible to do now, the technology has just developed to the stage where we will be able to do experiments to answer these questions. And that is what I want to tell you about today. So this slide, I was looking at the slide on the left, and it made me think about people trying to make sense of the cosmos and who are we and where we are before we had the telescope. So I like to imagine people, I don't know, maybe sitting around the fireplace and looking at the sky and just seeing the stars, right? These white points. And from there, trying to make sense and make cosmological theories out of that. And it's very difficult when you don't have instruments. But then Galileo invented the telescope, and the telescope has developed immensely since then. I'm thinking about the latest telescope that we've just very recently been able to see their new images, which are breathtaking. They're amazing. And thanks to these progress with the telescopes, we've been able to learn that the universe is expanding. We've been able to see very far away into the early universe, and we came up with these fundamental questions that we were talking about. With it seems that there's something out there that we don't know what it is, that we like to call dark matter and dark energy and so on. And that's all thanks to the observations made by these very sophisticated instruments. Now, the same thing happens when you think about looking at the very small. So the Greek came up with the ideas of the atoms, but it's not until you construct a telescope, a microscope, and you look into it, you can make some more sensible theories of the microscopic world, atomic physics, and so on. So the point I'm trying to make here is that we first need the instruments, and then to make observations so we can make more meaningful theories. However, you can't make or build an instrument just out of the blue. You have to start with something, some pieces of theory. So that's what my research is about, is by taking those pieces of the puzzle that I mentioned before, in particular, quantum field theory in curved spacetime, and using those theories to propose new instruments that will allow us to look at physics at scales where quantum mechanics and general relativity should interplay. So when it comes to those scales where we will be able to learn from nature how to bring these theories together, we're worse than this hypothetical group of people looking into the sky that we were talking about before, because they could at least sit there and use their eyes to look at the sky. We are completely blind. When it comes to scales where quantum mechanics and general relativity interplay, we don't have any instruments and we don't have any experiments. So we're basically blind, and we're trying to make theories to describe that. And that's the theories would be string theory or loop quantum gravity and so on. There's more. But the important thing is that once we're able to build those instruments, we will be able to test which theories are right or which elements of which theories are to be rescued, and hopefully come up with better theories. So again, that is the main aim of my research. as I explained. And one of the things I want to tell you about today is how we use a Bose-Einstein condensate to develop new designs for new concepts of instruments, to look into these scales where we expect new physics. And this is very nice because Bose-Einstein condensates, I will tell you in a moment what they are, but they're very cheap as compared to some of the other instruments where we explore these scales or try to reach these scales like CERN or LIGO and so on. So they're small and they're cheap, so they hopefully will have some advantages. And I want to tell you more about why we think this will give us some possibilities. So when we think about this, let's talk a little bit about the scales. So when we think about quantum physics and general relativity, what comes to mind are small scales, like where electrons and atoms live, and then large scales from Earth and beyond. So when I studied physics, like a long time ago, people would say quantum physics is about the very small scales where, like I just said, electrons and atoms live, and it applies to just a very few particles. Whereas general relativity goes on from, let's say, satellites already have to be described, the physics on satellites using general relativity and beyond up to the observable universe. This is, of course, not really true also when you go to the big scales, because general relativity doesn't tell us about dark matter and dark energy. So obviously the theory has to be extended in that sense as well. But, this idea that quantum mechanics applies to the small scales and GR to the big scales is now completely blurred out, thanks to the new experiments. So a few years ago, China launched MICUS, which is a satellite especially purposed to do quantum experiments and distribute, operate quantum technologies like quantum cryptography to make a global network for quantum cryptography, for example. So when I studied my PhD, we were talking about experiments for entanglement, and these took place in tabletop experiments. And since then, the experiments have developed so much that now in the satellites, they are able to distribute entanglement across thousands of kilometers. So the entanglement is between photons, so still very small systems, but they can keep the entanglement across thousands of kilometers. So we're now starting to learn about what are really the scales of quantum mechanics beyond what we initially thought. So as I mentioned before, we know from GPS, for example, when you're at the scales where satellites operate, relativity kicks in. So the proper time on Earth is different to the proper time on the satellites due to the curvature of the Earth, that the mass of the Earth curves space-time, and that gives you different proper times. And our GPS here on our phones have to make corrections for that in order to give us the precisions that we get from GPS. But if we're going to be then distributing entanglement at these large scales, the interesting question that comes about is how does motion and relativity and the curvature of space-time affect entanglement? This is one line of research. I'm not going to talk about it today, but I've written a number of papers on how quantum cryptography, quantum teleportation, and different quantum technologies are affected by relativity due to the curvature of space. Another way, which I'm going to focus more on that you can test reach relativistic scales with quantum experiments is with large masses. So again, I was talking about how when I studied physics, people told me that quantum mechanics applied for a few particles, but we're going to see in a moment what's a Bose-Einstein condensate, but you can get up to 10 to the 10 atoms in a condensate. This is with hydrogen. So again, this sense of quantum mechanics only applies to small particles is been changed. Now you can have quite a mesoscopic system being in a quantum state. And one important line of research currently in experiments is trying to get bigger and bigger systems. and with more mass to see if quantum mechanics still holds. So the record is held by Markus Arndt in Vienna, where he's been able to put in a superposition molecules like keratin that have up to 10 to the 4 atoms in the molecule. And well, we want to get more massive systems. And one of the reasons why is because, again, addressing the measurement problem, we don't know why we don't see massive people, like in the scales where we live with more mass, we don't see people in superpositions of 2 different places. We don't see macroscopic objects in superpositions. And Roger Penrose and Diossi also proposed a very smart idea, which is to say, well, the difference between atoms and the macroscopic world is mass. So perhaps it's gravity itself, which is producing the collapse of the wave function when you have these superpositions. So he proposed a scale at which one should observe this collapse due to gravity. And the scale is when masses reach the Planck mass. So these are masses, let's say, corresponding to something like 10 to the 9 atoms. You should see the collapse of the wave function. So I've been working with my postdoc, former postdoc Richard, and with Roger on proposing experiments using a Bose-Einstein condensate to test these collapse scales. I'm going to tell you a little bit more about that in a moment. I'm just wanting to finish telling you about how current quantum experiments are reaching these relativistic scales. So this is perhaps the most interesting one. Quantum technologies are so precise that start seeing details about the fabric of space-time. So when I started to work many years ago with the ideas of, can we use quantum technologies to measure gravitational general relativistic effects, my colleagues working in general relativity told me, look, you're crazy. At small scales, space-time is basically flat and you're not going to find anything. However, what they were missing out is that quantum technologies are super precise. So let me show you how with this example. In NIST in the US, a few years ago, I don't know, maybe now it's not that few, it's more, maybe I forgot the data, but let's say it's something maybe like 10 years ago, Dave Wineland, who won the Nobel Prize for trapping atoms in an iron trap, took a quantum clock. So these are atomic clocks, the most precise clocks that we have on Earth. They used to measure time, but what he did is that he took the clock 33 centimeters upwards, and he was able to measure time dilation. So that means that because the space-time of the Earth is curved, when you put a clock here and one 33 centimeters up, you can see time dilation like in the satellite, but now at much smaller scales due to the curvature of the space-time. Now the clocks have improved so much that last year there was 2 beautiful papers in which the clocks reach precisions in which you can see time dilation at the millimeter scale. So now not 33 centimeters, but millimeter scales. Now this is very important because when you have an atomic clock is made of many atoms in a trap potential. So, but the sample that acts as a clock is in the millimeter scales. So if you continue to go more precise, you can see that the time at each slice in the sample of your clock is different due to proper time. So already now, the atoms on the bottom of the sample see a proper time different to the atoms on the top. Now, this might not be a problem when the atoms are all independent as they are now, because you can calculate mathematically the correction due to the proper time, and you can correct for that. So it's not really a problem. The thing is that scientists want to entangle all these atoms to make the clock more precise. But when you entangle all the atoms, you lose then the notion of proper time, of clock time, because which time are you going to use? The one on the top, the one in the bottom, if all the atoms are entangled? So that is a very interesting question that I'm also working on. And the first steps that we've taken in my group to try to address this question is with a light clock. If I have time, I'll tell you about it, but I'm not very sure I'll have time for that. But that our latest paper, the one here in the bottom, is addressing this sort of questions. So what I'm trying to say right now, or convince you that the latest quantum experiments, this very advanced quantum technologies, in different ways are reaching scales where they're approaching these interesting scales where you can expect both quantum effects and general relativistic effects to interplay. So we will very soon no longer be blind in that sense. We start getting the possibilities of proposing experiments and developing new technologies, new instruments to learn about physics directly. So, like I said, I'm going to focus on a Bose-Einstein condensate and tell you some of the things that we can do with that. So you trap many atoms in the potential. So when you can cool them down, there are many different techniques to cool them down. And when the atoms reach the ground state, they become completely delocalized in the potential. And they get some sort of sharp mode in frequency. But the interesting thing about the BEC is that when you are able to cool the BEC as close as you can to the ground state, so the coldest is in the picokelvin regime, so super cold, half a nanokelvin, something around those lines. So you have all the wave functions of the atoms in the BEC overlapping, and the whole thing behaves in a quantum mechanical way. So people were able to condense atoms like this already, I think, late 80s in people in NIST. And since then, there are many experiments taking place in the world using Bose-Einstein condensates. So my work with Richard and with Roger in that direction has been proposing to use a BEC and putting the atoms in a spatial superposition of two different positions to try to see if we can reach these large masses to test Roger's idea that gravity produces the collapse of the wave function. So this is very difficult because you need to produce a state that's called a noon state, all the atoms on the left plus all the atoms on the right. And it's quite difficult to do. And people are trying to do this with other systems, like, for example, with diamonds or with beads, and so on. But it's very hard to put these massive systems in a superposition because they're very hot. But the BEC is a very cold system, as I mentioned, in the picokelvin scales. So we think that the fact that they're very cold are good candidates to try to test this. And at the moment, we have already secured some funding to start doing the experiment. So I'm a theoretician, but I like to work with experimentalists. So the idea is that our group will hire the experimentalists to work also with Roger to try to test this, or with the let's say, advice of Roger and so on. So we're excited about moving a bit towards more the experimental side of physics in this direction. So the other thing that is interesting about the Bose-Einstein condensate is that different from the beads or the diamonds, which are solids, the BEC is sort of a gas or a fluid. So the atoms are not bounded. So atoms actually can tunnel from one side to another. So we're now using this tunneling effect or single particle effect to try to study the effects of gravity on the superposition. So the other thing that we did in this work is that Roger had only calculated self-gravity in the case of uniform spheres, but a BEC you can put in many different geometries and their density is not uniform. So we then showed that the fact that the density is not uniform and that you can use different geometries, this is going to help find, let's say, test if gravity produces the collapse, because the collapse let's say, prediction is highly dependent on the density and on the geometry. So that's what our work is about. And an important thing is that, well, the states die because of decoherence. So basically, when you have interactions of the environment with your system, this quantum superposition dies very quickly. So we did like a very in-depth study of all the different sources of noise and decoherence to see if we could actually study the gravitational effects in spite of these noise effects taking place as well. So now I'm going to, let me see how I'm doing with time. I think I still have time to tell you about this. So now we're changing a little bit. The thing now, I want to tell you about another line of research also using a BC. But in this case, what we're trying to do is using the atoms that are trapped to measure changes in the underlying space-time. So build something like a space-time probe. And this is work that I've done with my PhD students and some recent postdocs like Richard as well. So let me tell you first, how do people use cold atoms to measure the local gravitational field or gravitational effects? So the main, let's say, a scheme is called atom interferometry. So you take 10 to the 5, 10 to the 6, something like this atoms, but the atoms are all independent. And with lasers, you create an interferometer. So you make each atom go through 2 different trajectories in a superposition at the same time, and then they recombine. Now the trajectories are different, so they pick up a phase, and the phase depends on the local gravitational field. And that is what is used to make gravimeters and to measure gravity. So the precision is this equation here. This is in the acceleration, basically on the local gravitational field, goes like 1 over the number of measurements that you, the square root of number of measurements that you make, the mode number, and most importantly, the time of flight. So if you want to make an atom interferometer very precise, you need to make it bigger and bigger and bigger. Now, this is a problem because you might want, for some applications, like finding, for example, oil or resources, or even finding, in London, they don't know where the pipe work is under the city, and the city spends millions of pounds trying to find out where the pipes are. But if you could have an atom interferometer, like a gravimeter, a very precise one on your phone, that would be like a fantastic application to have. And also you could use it for archaeology, for anything that involves finding structures underground. So this is very important. But because the precision is this simple and depends highly on the time of flight, well, you could not shrink it without losing precision. So I call this a single particle detector, because although you throw at it, let's say 10 to the 5, 10 to the 6 atoms, they're all independent, and each atom on its own goes on a superposition. Actually, interactions between the atoms produce noise, and therefore in the lab, what people try to do is to prevent interactions to occurring. Then I also wrote here that the interaction is local because it occurs at the point where the 2 trajectories recombine. So I wrote here that this is interferometry in the spatial domain, because each atom goes into 2 different spatial trajectories. And like I said, it's limited by the time of flight. And I wrote here, this is compatible with Newtonian physics, because the way that we describe atom interferometers is using the Schrödinger equation. And we talked about before how in the Schrödinger equation, time is absolute, just like in classical physics. So Newtonian gravity is compatible with quantum mechanics in that sense. However, if you wanted to now go beyond the Newtonian gravity into general relativity, then you have a problem, because your atom interferometer is not Lorentz invariant, and you have a number of problems with your inner products and so on. So what we've done in my group is we proposed an alternative for measuring gravitational effects. Okay, let me maybe go back, in which instead of having the atoms in free fall, we're proposing to trap them in a potential and create a BEC. So in this case, you do have interactions. So in atom interferometry, you try to avoid interactions. Here, you're going to use the interactions that you get. The atoms start colliding, and they produce excitations that are called phonons. So you can imagine the BEC being like coffee, let's say, and then the phonons being the little wiggles on your coffee, the little waves on your coffee, and those are quantized. So they are a relativistic quantum field, and they're produced basically by the collisions between the atoms. So basically there's entanglement underlying there, and we're going to exploit this entanglement. So this is a different scheme on how to do interferometry, because we're not using spatial states, we're using states that are sharp in frequency, but the atoms are completely delocalized in this potential. So that's why we call it frequency interferometry. So in spatial interferometry, the precision is limited by how big the system is. So the bigger, the most precise. But here we're not using spatial interferometry, we're using frequency interferometry, which basically means time interferometry. So you, in order to have more precisions, you just need your states to live longer. So that's sort of the price to pay, or what you need to do is have states living longer. But the amazing thing about this is that then you can shrink the system. You can make it very small. And I recently have a patent on how to measure the local gravitational field and its gradient using this idea, because now in principle, you should be able to put a quantum gravimeter one day in your phone. At least it's now possible. So I had here some pictures on how in atom interferometry, people are trying to measure things very precisely, making them bigger. So for example, my colleague Philippe Boyer flew an airplane in free fall. He did the experiment, but flew the airplane as well. He leads the experiment to get these long times of flights. And another of my colleagues, Ernst Russell, throws a BC on a tower. This is the Einstein Tower, to get again these long time of flights. And also Philippe has a super big experiment underground, which is an atom interferometer, and each arm is 300 meters long, something like that. So as you can see, the tendency is to go bigger and bigger, but I want to go smaller because of the applications I just mentioned. So using this idea of atom interferometry in the last years, my group has proposed many applications. So one of them, and one of my favorite ones, is how could you use this frequency interferometry to measure gravitational waves. So I'm going to tell you a little bit more about that. But we have also developed some ideas of clocks in the interface of quantum mechanics and general relativity, some searches for dark matter and dark energy. Like I said, the two ideas for measuring gravity and its gradient, which are patent, and we're working on curvature and other space-time parameters. So it allows you to do quite a lot. So as I said, we use quantum field theory in curved space-time in this proposal, instead of using just quantum mechanics. So as far as I know, these are the first sort of proposals for technologies using a theory like quantum field theory in curved space-time. Now, this theory has not been demonstrated in the experiment yet. At CERN, people have demonstrated quantum field theory, but not in curved space-time. So the proposal that we're putting forward would not just allow you to, for example, maybe detect gravitational waves, but also test some of the key principles of quantum field theory in curved space-time in the lab for the first time. So let me tell you briefly how it works. So when you put all the atoms in the ground state, they obey a classical equation, which is called the Gross-Pitarevsky equation. And the wave function you can write down as this mean field, which is the part of the wave function that corresponds to the ground state that obeys the equation I just mentioned. But because the atoms collide, then you get perturbations on the ground state, and those are called your phonons, or density fluctuations. They have many different names in different papers. But the important thing about them is they're like you can imagine, like the little waves that are quantized, and those obey a Klein-Gordon equation. So this is a relativistic quantum equation. So it's very nice because you can have like the Lagrangian of the BEC written in a fully relativistic way. So this is how the equation looks like. I'm not going to go more technical than that because I know that people listening to this talk are in physics but in many different fields. But I think what I want to say, which is nice, is that you can describe the physics of these atoms in the potential in a fully relativistic way. So you can see here the underlying metric of the space-time, and these are some corrections to the potential of the BC due to relativistic effects, and these are the collisions between the atoms. So I'm going to, because I'm running out of time, Melissa, I have 50 minutes, is that right?
Yes.
Okay, great. Basically, we use the Klein-Gordon equation, and here you can see some of the mathematical tools that we use. If you want to ask me in the questions more details, we can go back, but I'm going to go fast through the technical bits. So the main thing that we're going to do is that we're going to use these phonons that, again, I said they're sharp, they're quantum states, they're sharp in frequency and completely delocalized in space. And we're going to pick two different phonon modes, two different frequencies that if you sum them up, they resonate with, let's say, for example, a gravitational wave. So this is how the metric that the phonons see in the Klein-Gordon equation look like, and it looks very much like the flat in the but with the speed of sound replacing the speed of light. So basically, the BECs, because they're made of atoms, the excitations propagate at the speed of sound, which is related to the collision rate of the atoms. I don't want to go very technical, so that's why I like, oh, let me not jump some of the details here. So you can study how these phonons behave, these quantum states behave, if you're now changing the underlying space-time due to, for example, a gravitational wave. So that's what we studied. And we then looked at how, if we prepared a given quantum state at the beginning, how that state would be changed due to the passage of the gravitational wave. So this is sort of the proposal. You take, these are all the atoms in the ground state that we call the pump, and then you get the two phonon modes that are your frequency interferometry, and then you do some quantum gates to mix these states up. Then comes the gravitational wave, that is this block here. And then you close the interferometric protocol by doing the inverse transformation, and then you measure. That's like roughly how it works. And we use quantum metrology to estimate how precise the system is. So in quantum metrology, you basically study quantum states. There are some good states and some bad states that you can prepare your state in. And then you see how, let's say, for example, if the gravitational wave comes by, it encodes the amplitude of the gravitational wave on your states. And quantum metrology gives you strategies on how to prepare the state and how to measure it such that you can estimate that parameter in the best possible way. So in quantum metrology, you find that the precision in estimating, in this case, the amplitude of the gravitational wave is bounded by the number of measurements that you make and a figure of merit, a quantity that's called the quantum Fisher information, that basically tells you information on how much the state changes. So if the state changes little due to the gravitational wave, then the precision is going to be small. But if the state changes a lot, so that's where picking a good state comes in, then the precision is going to be very good. So this is what we use to study how good the precision is. And we find our results. I showed you the precision for the gravimeter, which was very simple because it basically depended on the number of measurements and the time of flight. And here you can see it's a very complicated equation. It depends on the mass of the atoms, on the number of atoms in the ground state, in the size of the different dimensions, in the lifetime of the phonons. Anyways, it's more complicated, but the precisions are very high. So these are all the constraints. They have to satisfy also a lot of constraints that, for example, that you're under decoherence, that you're with weak interactions and so on. So that it just becomes very technical. But the important thing is that the the precisions that we predict are very high for high frequencies. So this is LIGO and LIGO. These are the two amazing apparatus that are being used to measure gravitational waves. So you know that these are interferometers that are very big, no? So each arm is like 4 kilometers big with lasers, and they use mirrors that are like 10 kilograms and so on. And when they go into high frequencies, they lose precision. So we propose using this atom interferometry to go to high frequencies. So in a way, we are not competing with LIGO. We're complementing what they could do, because in principle, when we build these detectors, we will be able to go to high frequencies, where you might actually, at these high frequencies, you don't usually have gravitational waves such as the mergers of black holes, but you might have something like dark matter. So this sort of system would be good to do searches of dark matter, for example. So this is a little bit of an unfair comparison, because we're comparing the experimental results of LIGO, and these are just our theoretical predictions. But you can see that the theoretical predictions show that the sensitivities go very high at high frequencies, and this could be very interesting to search for new physics. So this is about dark matter. So people were looking for dark matter in CERN, and this is this pink region, and they were not able to find anything. And if they wanted to go beyond this, they would need a bigger accelerometer. And you know, that would be like many billions of euros or dollars or whatever, very expensive. So people working in the field are trying to look at, these are single particle scattering effects. So now they're looking at collective behavior of the dark matter and seeing if they can study this collective behavior at lower energies. So we saw that our detector in principle would be able to search for dark matter at these energies here, which are much lower. So this is perhaps a good proposal for a new technology that uses both quantum mechanics and general relativity to try to find these effects. So I think, let me see how I'm doing with time. LIGO is very big, and the precision depends on delta L. It's how much the arm changes due to gravitational waves divided by the length of the arm. This is what LIGO uses to detect gravitational waves, the precision. But in our case, we're not doing spatial interferometry, we're doing frequency interferometry. So ours doesn't depend on that. That's why it doesn't have to be big, as I mentioned before. What we're using is resonances. And the first apparatus that people built to try to detect gravitational waves also used resonance. They're called Weber bar. And this didn't work because they were very hot. So when they were built before LIGO, they were cooled down to 4 Kelvin. However, a Bose-Einstein condensate is 10 orders of magnitude colder. So basically what we're proposing is to build some kind of quantum Weber bar. Well, I'm going to jump some of these things there because I just saw Melissa, and I guess that means I'm running out of time. So let me see, perhaps this is about the clocks, but it's fine. I don't need to tell you about that. I think I'm just basically going to jump. This is our patent that I mentioned for measuring the local gravitational field using the Bose-Einstein condensate. But I'm just going to jump to my last slide to sort of conclude and put the ideas together. So I think that the takeaway message from today that I wanted to put is that quantum technologies have advanced very much. And from different ways, let's say long distances, like in the satellites, or high precisions, like with the clocks and the quantum technologies, and the large masses, they're reaching these scales where quantum mechanics and general relativity are predicted to start to interplay. So I think, as I said before, we're coming to a very interesting time in which we will have for the first time experiments to help us guide our theories. And I tried to convince you that a Bose-Einstein condensate is a very good candidate system to try to start testing a number of interesting things at the interplay of quantum mechanics and general relativity. And I finish here just by thanking again the organizers and also saying I'm looking for postdocs and PhD students. So if you want to get in touch, if you're interested in joining the group, please do. Thank you very much.
Thank you, Dr. Fuentes, for your amazing talk. I think this is why we become physicists, right? it's like for me it's crazy. I mean, for me as an experimentalist, it's crazy, like for real. There are some questions in the chat. I would like to address them. So Achabinok says, number one, is there a prospect of studying or devising experiments related to this via non-Hermitian phenomenon?
Via non-Hermitian, I have heard about some proposals for experiments using that. Maybe a good author to look into relating to that could be Czeslaw Bruckner. I think he might have in his work some things related to that. Let me see if I think of someone else, I'll let you know. But I have seen some proposals in that direction. Although I'm not terribly familiar with them, I would advise to have a look at Czeslaw Bruckner's work.
Okay, there's another question as well from Achabinok. So he says, maybe a stupid question, which is not, but if we are somehow able to achieve a theory of quantum gravity, how would it affect or change technology?
Oh gosh, that's a nice question, but it's always a little bit like almost impossible to imagine, right? So think about if you can, I lived when there was no internet, right? So I grew up in the times where there was no internet, and then the internet came about, and it was almost impossible to imagine all the sort of things that we have now. Maybe you could imagine some of the things, like, for example, we will be able to see each other when we talk by the phone. And when I was a little girl, I used to think like, what? That's insane. And well, now we have it. So when we're able to do those technologies, it's hard to imagine how much we could push. But I have something very nice to say about it, I think. Look, if you think about the technology that we're even using right now to communicate, that it's amazing that we can see each other and so on. All of this, including the internet and so on, is the technology that is a product of classical physics. Because, okay, we use some quantum elements to it because transistors use quantum mechanics, but this is what we use called quantum technologies 1.0. Because you have some elements like lasers or like transistors that operate thanks to quantum mechanics, but you're not really using quantum technologies in the sense that we're not exploiting entanglement or squeezing or anything like that. So all the technologies that we have right now are the products of classical physics. And we're at the brink of starting to see the technologies of the microscopic world, quantum mechanics, and general relativity. So these are, like the theories that are not aligned with our experience. The reason why understanding quantum mechanics can be very hard is because it is not in harmony with our everyday life and our intuition and so on. So we're going to start seeing the technologies of all those physics which is not aligned with our intuition. So it's just mind-blowing, I think.
Thank you for your answer. There's another question from Santiago Alvarado Orozco. He says, thank you for such an interesting and great conference. If gravity was the reason of the state collapse, in your opinion, how would that change the way we see gravity?
So we would have to change, maybe not gravity. We would have to change quantum mechanics. That's what Roger actually thinks, no? Because Roger thinks that we should keep the principles of general relativity, but because of the measurement problem, we would have to change quantum mechanics. I guess what we would have to do is keep quantum mechanics as it is with low mass, but then when you start approaching the large masses, then we would have to build a new theory, taking both some elements of quantum mechanics and general relativity to put them together. But, you know, not even Roger Penrose has been able to do that. When you see the work that he did, it's just like an educated guess. There's no theory, there's no details. He just says, well, there should be a conflict here because of these reasons. And then we can do an educated guess using an uncertainty principle to estimate these scales, but he doesn't have a theory. Now, the important thing is that from the experiment, we would be able to learn some extra things that hopefully would allow us to make a new theory.
Okay, we have another question from from Cliff. Oh, sorry. So from Cliff Ori. So it says, can quantum entanglement violate relativity and thus allow faster light exchange from one particle to another?
So no, that's a good question, very good question, and it's also quite confusing, and it has a nice answer. So it doesn't violate, entanglement doesn't violate general relativity for the following reason. Imagine that you take two spin particles and you entangle them in a Bell state. So they're both up, and down, and you separate them. Now, if you measure on this side, it's going to collapse the state of that. So if you measure up, this is going to, when you measure on this side, is going to be up, and when you measure down, it's going to be down. So it looks like something has occurred instantly. Well, the measurement is affected, but you can actually, this is what you see in the simplest protocol for teleportation, is that you cannot send a signal using that, because maybe it's a little bit hard to explain in such a short time, but you could see into quantum teleportation protocol, which is very simple and is using what I'm saying. If you wanted to send information, at least Alice would have to tell Bob which measurement she got, so Bob can reconstruct the state. So there has to be some classical information going through. So, and the only way to send classical information is the fastest would be with a photon, so you don't violate general relativity.
Okay, we have another two questions. So Andre Marin says, thank you for your astonishing lecture. How could we use BEC in measuring dark energy?
Oh, yes. Thanks for your question, because I was trying to tell you about that, but I wasn't very able to cover so much information. So with dark energy, there's a very nice experiment that has been done already in NASA in the US and in Imperial College, proposed by a colleague of mine in Nottingham, Claire Barrage, in which they had atom interferometry. So I did tell you about atom interferometry in the talk today and how it works. What they do is that they put an atom interferometer, but they put it inside a metallic shell. So the shell basically screens of every electromagnetic, every other force, what happens inside. So that's just to screen. And then they put a mass with the interferometer, and that mass is a source of dark energy. So if dark energy exists. So Claire made some predictions of how would dark energy change the interferometry scheme to measure it. And what we've done is to say, okay, instead of having the atoms in free fall, let's trap them, create a BEC. And then what we're able to see is that the metric in which the BEC lives is different if you have a source of dark energy. And we studied in a paper, so that you can look it up. If you put dark energy or chameleon fields or something like that, and my name, you can see the details. But basically what we show is that the metric, if you move the source, would produce changes in the phonons of the BEC, like very roughly.
Okay, we have a final question and then just a comment. So Cesar Martinez says, what an amazing talk. What do you think would be the implications if the entanglement effect could be conserved for objects with bulk mass?
With large mass?
Well, he says for objects with bulk mass.
With what mass, Melissa?
Bulk, B-U-L-K.
Oh, with bulk mass. I don't know. I think what I am understanding is what would be the implications if we could have entanglement with massive systems, I guess.
Yeah, Cesar, if you want, you can speak up and ask your question.
Well, if not, I'll make a comment on that, and he can correct me if I understood incorrectly his question. But what I understand is that because we don't know if we can have neither superposition or entanglement with massive systems, right? So if we do an experiment and we find that we can have entanglement and superposition with massive systems, that basically would be groundbreaking, because it would mean that we can have quantum gravity at those sort of mass scales, which is somehow something we don't expect, because we somehow expect to get quantum gravity at the Planck length, which are extremely small scales. So it would be incredibly surprising for us to have quantum gravity effects at massive scales. So we would have to rethink the way we looked at quantum gravity and the whole physics itself. It would be groundbreaking. Yeah.
Okay, and finally, we have a comment from Achal Binaut. He says, would it be possible to contact you via email? Thank you so much for taking the questions and those insightful answers. Thanks for such an interesting talk.
Thank you. Yes, of course, do. I've always had to take some students also from Mexico with CONACYT. I don't know if CONACYT is still giving scholarships to do PhDs abroad in physics, but I have so far 3 from CONACYT who's been amazing to work with and so on. So for other international students, it depends, because the UK with Brexit has made things more difficult. But in any case, get in touch and we might be able to find some solution.
Yeah, sure. I'll be happy to share your email if you want.
Yes, of course.
I can share your email via Discord, so you can all have it and send her an email if you want. So I would like to make an announcement before wrapping up. So we are making a change in the schedule. Instead of moving on with the next activity, which was planned to be the social activity, so virtual museums, we are moving to lab tours. If you go to Gathertown, you can visit the lab tours. There's a room named lab tour, so please go ahead and join Gathertown. And after that, you can all join the social activity, so virtual museums in Mexico. So once again, thank you so much, Dr. Fuentes, for being here, for your participation in ICPS 2022. It's such an honor for us to have you here.
Thank you very much. On the contrary, it's a great pleasure. I'm very grateful. And everybody for your attention.
Yeah, thank you so much.
Thank you. Bye.